Hello and welcome. So today we will do a fun exercise. We will try to understand logistic regression using Excel. So this will also give us an understanding of gradient descent along with logistic regression. Okay. So here are the two most important formulas that are required to understand logistic regression. One is the loss function. Here x is actually the predicted value after applying the sigmoid function. Okay, and this is the gradient of the loss function. Okay. So let's see. Okay, this is our data. Okay, so we have marks of students in two subjects, and we have whether the student was later placed in some job or not, 1 for placed and 0 for not placed. And we want to create a model which will predict, given marks of another student which is not in this record, given marks of a new student in these two subjects, this model could predict whether the student will get placed or not. Okay, so the first step, we add the bias terms. You can see in column C we add the bias terms and we normalize each of these columns. Okay, so we use this formula for normalization. We subtract each value by the mean of the corresponding column and divide it by the standard deviation. Okay, and then we take some weights. The weights are, we initialize the weights as 0. So eventually we want to keep this weights updated in every iteration and find weights which, when multiplied with the bias scaled marks 1 and scaled marks 2, will give us an indication that whether the student will be placed or not. So first we do a dot product of this W with the X, our X, where X is bias into this marks. Okay, this matrix. Okay, and here, so we get the Wx. If you see the formula of Wx, it's a matrix multiplication of this matrix with this column matrix. It's a vector actually, so we can consider it as a column matrix with 3 rows and only 1 column. Okay, and those gives these values. So it's 9 cross 3 into 3 cross 1. I can write it down here. We know the 9 cross 3, 9 cross 3 and 3 cross 1 gives us 9 cross 1. Okay, and that's what we got over here, the 9 cross 1. Okay, okay. Now after we did that, we want to find the sigmoid, because with any weights it would give values not within 1 and 0, and we want to clip the values between 1 and 0 using the sigmoid function. For that I calculated in 2 steps. First I calculated the exponential and then I calculated the sigmoid as 1 by 1 by 1 plus h3, and h3 is e to the power minus x minus Wx actually. Okay, so this gives our sigmoid output. So this is our original f and I is our predicted value. So predicted value is now at the middle. Okay, with these weights we predict these values, and what we want to do, if it's an actual 1 and our prediction is closer to 0, we want to maximize the error, and if our actually 0 and the prediction is closer to 1, we want to maximize the error. That's why we have this error function which does the job, and this is the derivative of the error function which we are going to use to update the weights. Okay, so first let's see what is the error with this using this formula again. Okay, so for each column this calculation is used. Here x is actually the sigmoid value, so y minus so this is y is this and x is this. For each column have done this for each row, and 1 minus y into log 1 minus x. So this gives this value and we sum over it and take the average. So this is our error with these random weights, or this weights initialized to 0. Now we calculate the error gradient in the same way. So this is our y predict again, and this is our y, and we use this formula. So first we do just this much, y minus y predict. Okay, and then multiply. This is a matrix product, not a dot product, with each of the x's. Each of the x's are the bias, scaled marks 1 and scaled marks 2. Okay, and when we multiply with each of these x's, we get 3 columns, right? For this one multiplied by this one multiplied by this one, and another this one multiplied by this one. Okay, and the sum values are the DWs. That is, when we sum over each of the columns, we get the gradients, that is the values by which the weights needs to be adjusted. So these 3 weights needs to be adjusted by these 3 values. Let me put it over here. Okay, the same values are just copied over here, and we will do W minus alpha times, which is the learning rate. We have taken as 0.01 DW. Okay, and by doing that, by subtracting this alpha times from this current weights, we get the new weights. Okay, these are the new weights now. So the 0 minus alpha times this gives this, 0 minus alpha times this gives this, and this one gives this one. Okay, so now we have to, this is end of iteration 1, and at the end of iteration 1 we updated the weights from 0 to here. Now we do repeat the process in iteration 2 but this time with our new weights. These are the new weights. Instead of this, we will use these weights, and this is our this is what happens with these new weights. We see this is the error now, and you can see this error has reduced to this one, 0.301 to 0.300. okay, and with this one we get the new gradients now, which are these. We copy it over here, and we adjust the weights again with these weights with the new gradients, and get again another set of weights. Okay, with which we will start our iteration 3, and we see in iteration 3 our errors are further reduced. In this way, the error keeps on reducing in each iteration, and we say after 400 iterations we get these as the final weights when our error is minimum. Okay, and now we have say a student, an unseen student with values with marks 85 and 85, and we want to predict whether that student will get placed or not. So what do? We again add the bias term, and we normalize the values, but we use the mean and the standard deviation from here to normalize these values here, and we take a dot product of this with this. Let me use the pen. Okay, so we use the dot product of this with this to get, what do we get here? We get the Wx when using the dot product, and then applying the sigmoid over this, we get here. We apply it in 2 steps. We apply the sigmoid. Okay, and then so it's 0.6, which is closer to 1, so we say it's a 1, and this student gets placed. However, it can be noted here that we are taking the threshold as 0.5, and if you use a logistic regression library and do a predict, it will use the threshold of 0.5. However, you can take the probability yourself and take a different threshold, maybe 0.6 or 0.2 or 0.7. Why you will take that, I'll come to that in one of our next videos. So you might choose, so you can use the predict proba instead of predict, and it will give you this probability, and you can use a different threshold. Maybe you can call this a 0 based on your performance on your test data, that if you take the threshold 0.7, the predictions will be better in future. Okay, so you can choose to have a different threshold. Okay, and another point here, we again we are doing the logistic regression with a linear function, right? So we can again choose to do a polynomial function. In that case, we have to raise this to a power of 2 or 3 and use the SciPy library to raise it to polynomial features, and then do the same logistic regression. And in that case, now in this example, our separation line or our boundary line is a straight line, and if we raise it to some power, it won't be a straight line, it would be something of a polynomial line. Okay, so what is the boundary line equation from here? We can take the weights, and it's minus 0.20 plus 1.40 into marks square 1, and minus 0.30 into or 31 into marks underscore 2 equal to 0. So this is the equation of our boundary line. Okay, so let's see how we can draw the boundary line. And this is if we rearrange the equation of a boundary line and express marks 2 in terms of marks 1, it should look like this. Marks 2 is minus c plus m1 into marks 1 by m2, where okay, and these are our scaled values of marks 1 and marks 2, which we will require to plot this. Okay, and these I have created a range of x values to plot the line. So by this range covers the entire x values. So I have taken it from minus 1.5 and with a 0.1 increment till plus 1.5, and the corresponding marks 2 values I can calculate using this formula. Okay, and we have our c final weights, which we can interpret as c, m1 and m2, and using these values and these values I write down this formula to calculate the y values for my line. Okay, and here are the y values. Now I can select these x and y's and go to the plot. Here it's in the insert, and under insert you can find the scatter plots, and first I'll select this one to plot a line, and here I plot the line. This is the line, and then I select this one, okay, and these values, and use this scatter plot and here. And now I combine these two, I copy these plots, just the Control C and from here and Control V over here, it would give this one. Okay, so this is the boundary line, and these are our two sets of two classes, one on this side on the left side and one on the right side of the boundary line. So now you can see that we can plot a boundary line of a classifier, and the entire example is demonstrated with Excel. I hope that was interesting and intuitive, and that gives an idea, a clear idea of how logistic regression works. Okay, thank you. See you in the next video.